Hello everyone, welcome to a lesson on support vector machines. Support vector machine classifiers are often regarded as one of the greatest linear and non-linear binary classifiers. SVM original algorithm was developed in 1960s in AT&T. Later on in 1990s, a kernel trick was introduced, as you will see in further slides, which enabled to apply SVM on non-linear classification problems as well. SVM is a supervised learning algorithm. So if you're familiar with supervised and unsupervised machine learning algorithm, all that it means is SVM requires target label during training time. An SVM can be used for both classification as well as regression. However, the use of SVM for regression is not very well documented and it's most suited for classification problems. Moving on, SVM is a discriminative classifier. So what does it mean? So the goal of SVM is to find a hyperplane that best divides the dataset into classes. Here we are mentioning two classes. That's a binary classification problem, but SVM can also be used for multi-class classification problems. As you will see in the next slide, the goal of SVM is not only to classify the points correctly, but also to find a hyperplane which has the largest margin. Applications of SVM can range from anomaly detection, handwriting recognition, to intrusion detection. In fact, the famous MNIST dataset was initially demonstrated using SVM. One of the power of SVM that it can solve both linear as well as nonlinear problems. You will see about this in coming slides. A natural question that comes in mind is why they are called support vector machines. So, in fact, the name comes from an analogy that data is a set of forces acting on a hyperplane to keep it in equilibrium. So, drawing from this analogy, we can think of support vectors as the training instances that support or hold up the optimal hyperplane. The basic intuition to develop here is that the more farther SV points or the support vector points are from the hyperplane, more is the probability of correctly classifying the points in their respective classes. So as you can see, they are very critical because if the positions of the vector changes, hyperplane's position is altered as well. So the question that comes into mind is why we require another algorithm, right? So while many algorithms can be used in machine learning framework, each have its own advantages, disadvantages, unique characteristics, and it's important for data scientists to understand the algorithm before applying them to solve important business problems. For example, perceptron algorithm classifies the data by creating a boundary that separates the two classes. Linear regression tries to find a best fit line. Logistic regression, on the other hand, tries to find a sigmoid curve that best classifies the points. In each of these algorithms, there is no guarantee as to how good the decision boundary is, right? SVM basically takes the idea of classification a bit further by guaranteeing a best bound decision boundaries. That is like the decision boundary which is as wide as possible. You will see about this in coming slides. Continuing from our previous discussion, in the picture you can see two decision boundaries and it's classifying the points correctly, the blue dots and the red dots. The problem is that there can be infinite number of decision boundaries that are possible. The perceptron algorithm could produce any one of such decision boundaries and there is no indication to determine which decision boundaries is the best. This is important because during testing, the model will see unseen data and it needs to generalize well in order to classify the points correctly. So you must be wondering what is this term hyperplane? Hyperplanes are planes in a lower dimensional space than the given input data. Hyperplanes separate the data into classes. If a space is three-dimensional, then hyperplane will be two-dimensional plane. Likewise, if a space is two-dimensional, then hyperplane would be one-dimensional line, as illustrated in the picture below. In SVM, the goal is to maximize the margin between the data points and the hyperplanes. These data points are called support vectors, and we will read about these support vectors in the coming slides. As mentioned before, support vectors are those data points that are nearest to the hyperplane and which help in orienting it. Support vector machine can also be called as the data points on the basis of which the margins are calculated and maximized. In the picture below, two support vectors are labeled. As mentioned before, the most intuitive way is putting in the wider street that separates the positive samples from the negative samples. Therefore, to separate, the fittest way is to find the widest street approach. That is the street that is as wide as possible, as shown in the picture below. Many a times, the sample data points are so dispersed that it is not possible to separate them using a linear hyperplane, as shown in the picture below. It would be interesting to see how SVM solves such problem. Let's see in the coming slides. Answer to the problem is projection. More specifically, SVM uses a function that maps the data to higher dimension where data is separable. In other words, SVM uses a function which transforms a low dimensional input data space into high dimensional space. It converts non-linear separable problems into linear separable problems by adding more dimensions to it. We'll talk about this function in a moment. In the picture below, green labels and red labels are not linearly separable in a 1D space. So instead, a function is applied and they are converted into a two-dimensional space. And now, as you can see, they are linearly separable. The concept mentioned before can also be explained using another simplified example. Imagine that there are two sets of colored balls sitting on a sheet and they are not linearly separable. And the sheet is lifted suddenly, launching the balls into the air. While the ball are up in the air, you use the sheet to separate them. This lifting of balls represents the mapping of data into high dimension. This is known as kerneling, and we will talk about this in coming slides. The picture below shows green labels surrounded by red labels, and in no way this data can be linearly separable. Let's see how SVM tackles such problem. So as done before, we use a function that maps the lower dimensional data points into higher dimensional space. And it elevates our data points into higher dimensional space where they can be linearly separable. And we find a hyperplane that classifies the data points into two distinctive classes. Then we will project our data points to the initial dimensional space using another function. This is illustrated in the picture below. As we have seen, higher dimensional transformation can allow us to separate data in order to make classification predictions. However, if your problem has thousands of features, then this becomes impractical because of the computational cost. The kernel trick provides solution to this problem. The trick is that kernel methods represent the data only through a set of pairwise similarity comparisons between original data observations instead of explicitly applying the transformations and representing the data by these transform coordinate into higher dimensional features. As shown in the picture, the blue and red dots are not linearly separable, but using a polynomial kernel, they can be linearly separable in a 3D space. The first kernel that we are going to talk about is the linear kernel. Linear kernel, as the name suggests, is used when the data is linearly separable. It means that data can be separated using a single line. It is one of the most common kernels to be used. It is mostly used when there are a large number of features in a dataset. Linear kernels is often used for text classification purposes. Training with linear kernel is usually faster. We will see the decision boundary for the linear kernel in the next slide. The picture below shows a SVM implemented with a linear kernel on an iris dataset with only two features, sepal width and sepal length. The equation for the linear kernel is given below. Here, W is the weight we want to minimize, X is the data which we are trying to classify, and B is the coefficient estimated from the training data. This is the equation which governs the decision boundaries for the linear kernel SVM. The next kernel that we are going to talk about is the polynomial kernel. Polynomial kernel is more generalized representation of the linear kernel. It is not as preferred as other kernel functions because it is less efficient and it's less accurate. In the picture below, polynomial kernel is shown. It is non-uniform in nature due to the polynomial combination of base features.
Polynomial kernel is a more generalized representation of the linear kernel. It is not as preferred as other kernel functions because it is less efficient and accurate. In the formula, the star here shows the dot product of both the values, and D denotes the degree. Fxxi represents the decision boundary to separate the given classes.
Gaussian kernel is one of the most preferred and used kernel functions in SVM. It is usually chosen for nonlinear data. It helps to make proper separation when there is no prior knowledge of data. As shown in the figure, the green and the red data points are not linearly separable. Hence, a kernel trick is applied, in particular a Gaussian kernel trick, which projects the data into a Gaussian distribution, where the red points become the peak of the Gaussian surface and the green data points become the base of the surface, making the data linearly separable. The RBF kernel is again one of the most preferred and used kernel functions in SVM. It is particularly useful when the data is nonlinear. In the formula given below, the value of gamma varies from 0 to 1. You have to manually provide the value of gamma in the code as a hyperparameter. And the most preferred value for gamma is zero point 0.1. The gamma hyperparameter of RBF kernel controls the distance of influence of a single training point. Low values of gamma indicates a large similarity radius which results in more points being grouped together. For high values of gamma, the points need to be very close to each other in order to be considered in the same group. Therefore, models with very large gamma values tend to overfit. Following visualization explain the concept better. The sigmoid kernel comes from neural networks field, where the bipolar sigmoid function is often used as an activation function for artificial neurons. It is interesting to note that SVM model using a sigmoid kernel function is equivalent to a two-layer perceptron neural network. There are two adjustable parameters in the sigmoid kernel, the slope alpha and the intercept constant c. We'll study about c shortly. When it comes to choosing the best kernel, there is no definite answer, since it largely depends upon the type of data you are trying to solve the problem on. Sometimes even the linear kernel works for you. However, usually it is seen that the Gaussian kernel is most widely used. In the next slide, you will see comparison of different kernels with three different datasets. In the given figure, you can see three different datasets and four different SVM applied to all the three datasets. In the first figure, it seems that the RBF Gaussian kernel does the best, followed by the linear kernel. In the second data set as well, RBF kernel does the best, followed by the sigmoid SVM kernel. While in the last data set, it seems again the RBF Gaussian kernel does the best, followed by the linear SVM kernel, and then the sigmoid SVM kernel. In all the three, polynomial SVM kernel is least preferred. By far, one of the most important hyperparameter is the C parameter. The C parameter tells the SVM optimization how much you want to avoid misclassifying each training example. For large values of C, the optimization will choose a smaller margin hyperplane if that hyperplane does a better job of getting all the training points classified correctly. Conversely, a very small value of C will cause the optimizer to look for large margin separating hyperplane, even if that hyperplane misclassifies more points. For a very tiny value of C, you should get misclassified example often, even if your training data is linearly separable. As explained before, the value of C determines the width of the margin. Large value of parameter C will lead to smaller margin. A small value of parameter C will lead to larger margin and hence less misclassifications. We can see the decision boundaries for different values of C in the figure given below. As with all supervised learning, there is a bias variance trade off. When the tuning parameter C is small, the classifier only allows a small bit of misclassification. The support vector classifiers will have low bias, but may not generalize well and will have high variance. We may overfit the training data if our tuning parameter is too small. On the other hand, if C is large, the number of misclassification allow has been increased. This classifier would generalize better but may have high amount of bias. Weight parameter can be used if the target variables class is imbalanced. A larger weighting can be used for minority class, allowing the margin to be software, whereas smaller weighting can be used for majority class, forcing the margin to be harder and preventing misclassified example. In the coming slides, we will be taking up a specific use case of telecom customer churn. This is a problem which most of the telecom operators face, in which the customers either stop or quit the service. In this slide, you see the first step, which is loading of the dataset. Here, each row represents a customer. There are a lot of features such as gender, senior citizen, partner, dependents, phone service, among others. The last column is the churn, whether a customer has actually churned or not. And its value can range from 0 to 1. 0 being no, 1 being yes. The second step is to initialize the model. Here, we make use of the sklearn.svm package to initialize the support vector classifier. Here, the random state controls the pseudo random number generation for shuffling the data for probability estimates. In this slide, we show the training phase. The first step is to divide the dataset into features, independent variable and the dependent variables. As we shown before, churn will become the target or the dependent variable and rest of the features will be the independent variables. We split the data into training and test set using the sklearn model selection train test split. Finally, we fit the SVM model using the fit function. Finally, after training, we do the prediction on the test data. And also we do the evaluation on the test data. Here we show the classification report derived from the sklearn metrics package. If you see here, we have precision, recall, as well as the F1 score being shown for different labels. There are certain things which should be kept in mind when working with SVM. In particular, copying of the data should be avoided as much as possible. Not only because it will slow the training time, but also because it will skew the way the model assigns the weight to a feature. Another thing is that the kernel cache size should be kept in check because it uses the RAM. And if you have a very large data set, it can cause a lot of problems. Finally, scaling should also be done for when using SVM because SVM algorithms are not scale invariant. There are a lot of advantages when working with SVM algorithm. It works very well on smaller, cleaner data sets. It also works very well with high dimensional data. SVM kernel, if chosen properly, makes SVM memory efficient because it does not need to memorize anything about the data. SVM is a versatile algorithm, as different kernel functions can be specified. Even you can specify your own custom kernel. SVM has certain disadvantages as well. It is not suited for larger data sets, as training time can be very high. Also, it's not suited when there is a lot of noise in the datasets, particularly when there are overlapping classes. Careful hyperparameter tuning is required to avoid overfitting. Sometimes SVM output is hard to interpret due to its complex underlying structure.